Hello, and welcome to Linear Algebra. This is lecture 14, and today our topic is linear independence. So last time, we talked about encoding messages in a way that detects and corrects errors. This time, we're going to talk about possibly the most important concept in this entire semester, linear independence. So a million years ago, when I was an undergrad, there was a professor who would teach linear algebra, and on the final exam, the first question was always define linear independence. And if you got that wrong, he would not grade the rest of the exam. Okay, so what is linear independence? Well, linear independence is about redundancy. So for example, let's say you're looking at the system of equations, x plus y is equal to 3, y plus z is equal to 5, x plus z is equal to 4, and then x plus y plus z is equal to 6. Okay, well, you might notice that if you add this equation with this equation with this equation, you get 2x plus 2y plus 2z is equal to 12. So if you know these three equations, you don't need to be told this one. Right, so the last equation is redundant. If the first three equations hold, then adding them guarantees the last. Okay, another instance of redundancy. Let's say I'm looking at the span of the vectors 1, 1, 0, 0, 1, 1, and 2, 5, 3. So this is the same as the span of 1, 1, 0, 0, 1, 1, right? Since the other vector 2, 5, 3 is equal to 2 times 1, 1, 0 plus 3 times 0, 1, 1. Right? So if you have these two vectors and you're forming the span, so you're taking all possible linear combinations, then you get the same set of vectors as if you start with these three vectors and you take the span, you take all possible linear combinations. Right? So you don't need this one if you already have these two. Right? Geometrically, right, in the first situation, we have a plane containing these three vectors, and we're seeing that we get the same plane if we just take the first and third vector. We don't need that second one. Okay, so here's a definition. Now we're mostly interested in linear independence, but an equivalent concept is linear dependent, and we're going to start by defining that first. So we'll say that a list of vectors, let's say a set, a set of vectors v1 through vn in some vector space, and let's say that n is greater than or equal to 2, is linearly dependent if for some I, vi is a linear combination of the vj's such that j is not equal to I, right? So we're exactly looking for redundancy. We're going to say that a set of vectors is linearly dependent if one of the vectors is redundant. You can obtain it as a linear combination of the other ones. Okay, that's if you have more than one vector. What if you have a single vector? Say a set with a single vector is linearly dependent. Right, so how could a single vector be redundant? Well, if and only if that vector is a zero vector. Right, so if you have the zero vector, then you didn't really need to tell me that. So that's the redundant setting. So a set with a single vector is linearly dependent if that single vector is zero. Otherwise, a set is linearly dependent if one of the vectors is redundant when you're thinking about span, linear combinations. Okay, so note, so that's great. Now we want a formulation that's more symmetric, that doesn't single out this redundant vector, but that is more symmetric. So notice that if vi is a linear combination of the vj's with j not equal to I, then vi is equal to a sum j not equal to I of a j vj for some aj in the field. And we can write this as 0. So let's just put the vi on the other side. 0 is equal to a1 v1 plus dot dot dot. At some point this vi shows up, so we'll put a -1 times vi plus dot dot dot, and then at some point you have a n vn. Right, so by putting it on the other side, I now have 0 on this side, and notice that I'm writing 0 as a linear combination of the vectors in the set. But importantly, because this one is not 0, this coefficient is not 0, this is a non-trivial linear combination on this side, right? So you can always write 0 as a linear combination of whatever set of vectors. You could just put all of the coefficients equal to 0. That'll do it. However, what's special here is that I'm writing 0 as a linear combination, and I'm not using all of the coefficients equal to 0, right? I have another way of writing 0 as a linear combination. So let me write that out. Thus, in this case, we can write 0 as a non-trivial linear combination of the vectors in this set. Okay, so let me double underline non-trivial, because you can always write 0 as a linear combination of vectors. That doesn't tell you anything about the set of vectors. But you can, it's not always the case that you can write 0 as a non-trivial linear combination of a set of vectors. Right? And in fact, this is going to be equivalent to linear dependence. So let's start with the other side. So on the other hand, if 0 is a non-trivial linear combination of the set of vectors v1 through vn, which is the same as saying that there are coefficients v sub I in the field. Here, let's spell that out. v1 through vn in the field, not all equal to 0, such that 0, the vector 0 is equal to v1 v1 dot 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 vn vn. Then this set of vectors is linearly dependent. Right? So how do we know? Well, the claim is that one of these is redundant. One of them can be written as a linear combination of the others. But if you have a non-trivial linear combination that gives you 0, it being non-trivial tells you that at least one of the coefficients is not 0. So let's say if vi is not equal to 0, then what I can do is I can take that term on this side and move it to the other side. And then, because this vi is not 0, I can multiply by its multiplicative inverse to get rid of it. Right? In fact, by a multiplicative inverse of minus bi, so that on the left-hand side, I'll end up with a 1. So I can end up writing vi vector as the sum, j different from I, of minus bi inverse bj times bj. Okay. And so you see that the ith vector can be written as a linear combination of the other vectors in the set. And so it's linearly dependent set. Right. This is important enough that I will write it out again. So thus we have shown a set of vectors is linearly dependent if and only if there are scalars in the field, not all 0, such that the sum of vj vj is equal to 0, the vector 0. Right? Sometimes we'll say linearly dependent over F. To emphasize the field. Okay. So having defined linearly dependent, let's define linearly independent. So we'll say that a set of vectors or a list of vectors sometimes, so the difference between set and list in this class is that a list has an order, whereas a set does not have any order, right? Sometimes we want to think of sets of vectors as coming with an order, so we talk about the list of vectors. Soon I'll want to take these in an order, so we'll use lists. So let's go ahead and say here a list of vectors, but this would be the same with set. Now I'll use round parentheses when I want to use list, and brackets when I want to use sets. So a list of vectors is linearly independent if and only if it is not linearly dependent. If and only if the only way that I can take a linear combination of these vectors and get 0 is if all of the coefficients are equal to 0. Okay, so that's what it means to be linearly independent. It means that if you write 0 as a linear combination, then you know that all of the coefficients have to be 0. Okay, so one place where we get lists of vectors is when we have the columns of a matrix. Right? So if A is the matrix whose columns are V1 through Vn, then remember we've seen that matrix vector multiplication can be expressed as a linear combination of the columns. So in this case, if I take these bj's and put them into a vector, then A times B is exactly this linear combination. And so A times B equals 0 is precisely saying that this linear combination of the columns is equal to the vector 0. So we can now translate this. The columns of a matrix A are linearly independent. Okay, so let's see. The columns are linearly independent if the only way you can make a linear combination of them and get 0 is if all of the coefficients are 0. Okay, that's the same as saying the columns of this matrix are linearly independent if the only way you can do a matrix vector product and get 0 is if all of the coefficients are 0. But all of those coefficients, those are the entries of this vector. So the columns of matrix are linearly independent if and only if the only element, the only vector in the kernel of A is the 0 vector, right? It's the same as saying that the reduced row echelon form of A has a pivot in every column, right? A is injective, right? So if you think about this in terms of linear equations, right, what you want to say is that if you have a solution, then you only have one, right? So what you want to say is that you never have free variables, right? Because free variables is how we end up with multiple solutions. You never have free variables means that all of your variables are pivot variables. It means that every column in the coefficient part of the augmented matrix has a pivot. Okay, so that's great. So this yields an easy algorithm to check if a set of vectors or a list of vectors is linearly independent. Right? So it's a very easy algorithm. All you do is you take these vectors and you put them as columns of a matrix, and then you find the reduced row echelon form of that matrix. Right? So for example, the set 1, 1, 0, 0, 1, 1, 2, 5, 3 that we looked at before is linearly dependent. Right? Let's go ahead and do the algorithm here just so you see what you would get. So in this case, if I put them in a matrix as the columns of a matrix, and I put this in reduced row echelon form, then, well, what I would do is first use this pivot to clean up its column. So I would end up with nothing happens here. Here, I would just subtract the first column, first row. So I would end up with this. And then nothing happened here. And then I would use this pivot to clean up its column. And so I would end up with 1, 0, 2, 0, 1, 3, 0, 0, 0. Okay, so notice, you remember this vector we found was equal to 2 times this one plus 3 times this one, right? So those coefficients are exactly what showed up here. And from here we see that this column has a pivot, this column has a pivot, but this column does not have a pivot. So we know that this set is linearly dependent. Right? Also, from here, notice that if I had truncated, if I had only put these 2 columns, then I would have found the reduced row echelon form by following the same steps. So I would have had this guy, and then I would have had this guy. And so I would have ended up with this reduced row echelon form in which every column would have a pivot. So I can say, but the set 1, 1, 0, 0, 1, 1 is linearly independent. Right? Directly from our algorithm. Of course, we can also just check this directly. Let's say you had a linear combination of these 2 vectors, and it was equal to 0. Right? Then, okay, so again, let me emphasize, it's always possible to solve this. It's always possible to solve this by putting both of these coefficients equal to 0, right? So that's known as the trivial solution. That one's boring. We want to know, are there interesting solutions? Can you solve this any other way, right? Not in this case. These are linearly independent. There is no other solution. And it's very easy to see this because if you do this, you would end up with A in the first coordinate, A plus B in the second coordinate, and B in the last coordinate, right? Okay, but if I'm supposed to get 0 in the first coordinate, that means that A has to be 0. And if I'm supposed to get 0 in the last coordinate, that means that B has to be 0. So the only solution here is A and B equal to 0. Okay, let's do another example. So the set 1x and x squared is a linearly independent subset of the continuous functions on 0, 1. Okay, so I'm going to take a linear combination of these and I'm going to set it equal to 0. Okay, so notice that my vectors are continuous functions. So when I set this equal to 0, when I set a linear combination of these functions equal to 0, it's the function 0 that I'm setting it equal to. Okay. Also, I want to emphasize, this is something that's going to come up over and over again. Every time you want to check if something is linearly independent, you're going to start the same way. You're going to take a linear combination, set it equal to 0, and then you want to show that the coefficients are 0. Right? So, indeed, if A times 1 plus B times x plus C times x squared is equal to 0, we want to show right? Notice, emphasize again, this is the function 0. We will show that A, B, and C have to be 0. Okay, this 0 is the 0 in the field. This 0 is the function 0. It's 0 at every x. Okay, but let's check that this is 0. Now, I have this function, and I know that it's equal to 0. So I know it's equal to 0 at every point. I want to show that the coefficients have to be 0. Okay, so now I'm allowed to do whatever I want to this function to try to figure out if it's equal to 0. So for example, let's evaluate at the point x equal to 0. If you evaluate at x equal to 0, then b times x is equal to 0 and c times x squared is equal to 0. So we just end up with a equal to 0. So that tells us a is equal to 0. What we could do is differentiate and then evaluate at x equal to 0. Okay, well, if we differentiate, this becomes just b. This becomes 2cx. Evaluate at x equal to 0, and then this is just 0, and we end up with b equal to 0. If we differentiate twice, and then evaluate at x equal to 0, we would get that 2c is equal to 0. So c is equal to 0. Right? So the conclusion, so the only solution to a times 1 plus b times x plus c times x squared equal to 0 as functions is a equal to b equal to c equal to 0. Right? And that's what we mean by linear independence. That's the only solution. Okay. Now, a particularly nice case is when you have just as many vectors in Fm as m, as coordinates. So note that if v1, vm are vectors in Fm, so that the matrix where I put these vectors as columns is square, then, okay, we can say that these are equivalent. The list is linearly independent, right? That's the same as saying, right, by our algorithm, that the reduced row echelon form of A has a pivot in every column. Okay, but now A is square. So that's the same as saying that the reduced row echelon form of A has a pivot in every row. Okay, but what does it mean if you have a pivot in every row? Okay, well, that means that if I want to solve AX equal to B, right, so I would form the augmented matrix where I put A and then I put the column B. And now I take this to reduced row echelon form. If every row of A already has a pivot, then when I have augmented, there's no way I'm going to end up with a pivot in the final column, because every row can have at most one pivot, and all rows are already spoken for. That means I will never have a pivot in the final column. Okay, but not having a pivot in the final column means that the system is consistent. It means that there is a solution, right? So this means we can solve, let's say, the system AX equal to B has a solution for any B, right? And that's the same as saying that the span of the columns is all of Fn. Okay, so we have this very nice equivalence. If you have just as many vectors as you have coordinates, then you get a linearly independent list precisely when the span is everything. Okay, now here's something that's really useful for proofs. We're going to call it the linear independence lemma. And so here's where it's actually useful to be working with lists instead of sets. So to have a set with an order. So here's the linear independence lemma. Suppose that V1 through Vn is a linearly independent list. Actually, let's look at the dependent case. Linearly dependent list. And let's say the first vector is not the zero vector. Then there is a k in set 2 to n such that vk, the vector vk, is in the span of the vectors before it, v1 through vk minus 1. Okay. So linearly dependent means that I can write one vector as a linear combination of the other ones. Okay, so what this lemma is doing, this is just to make it easy to prove things, is that it says, okay, put your vectors in order. Pick an order, doesn't matter which order. And let's say that the first vector in this list is not the zero vector. Okay, then it's always going to be true that one of the vectors can be written as a linear combination of the previous ones. Right? So this is easy to prove. I'm not going to prove it, but you can see a proof in the book. I mean, you can just imagine that, well, if I were to make it to Vn without being able to do this for any of the previous vectors, well, then Vn has to be a linear combination of the other ones because I've run out of choices. So, okay. But that's only the case if you've made it all the way to Vn without being able to do it for the other ones. It may be that Vn is not a linear combination of the other ones, but there was some previous one that was. But in any case, there is always one that can be written as a linear combination of the previous ones when you have a linearly dependent set. So here's a corollary. This is how we actually use it most of the time. Given a list, in a vector space with the first vector not equal to 0, if for each k between 2 and n, we know that vk is not in the span of the previous ones, then the set is linearly independent. Okay, so let's see an example of how you use this. Here's a theorem. This is a really fun theorem. Suppose that we have v1 through vk are eigenvectors of a linear map with distinct eigenvalues. So lambda 1 through lambda k, respectively. Then the set v1 through vk is linearly independent. Okay. So yes, you'll see this has a very cute proof. So suppose that the opposite happens. Suppose, let's put them in a list, so let's fix an order. Suppose these are, this list is linearly dependent. Okay, so since we know that v1 is not the 0 vector, since it is an eigenvalue, an eigenvector, right? Remember, eigenvectors are necessarily non-zero. Then the linear independence lemma guarantees that for some j greater than or equal to 2, Vj is in the span of V1 through Vj minus 1. Okay, so pick the smallest such j. Okay, so the linear independence lemma tells us that there will be a vector that can be written as a linear combination of the previous ones. Okay, well, if that happens, there has to be a first time it happens. So let's pick that j, right? The first time that happens. And let's write Vj equal to a1 v1 up to a j minus 1 vj minus 1. Okay, so this is going to come up a lot, so I'm going to give this a name. Let's call it star. Actually, I want all of this equality. Star. Okay, so I've picked the smallest such j. I'm going to get a contradiction, right? I'm looking for a contradiction because I'm assuming the set is linearly dependent, and I want to show that actually it's linearly independent. So I'm looking for a contradiction, right? So I'm going to use this smallest to get a contradiction. If I can find a smaller one, that's a contradiction because I picked this one to be the smallest. So here's how we're going to do it. First, apply t to both sides of star. Right? If you do that, then what happens? Well, t of vj is lambda j vj, right? Because vj is an eigenvector with eigenvalue lambda j, right? But all of these other vectors are also eigenvectors, right? With different eigenvalues. They're also eigenvectors. So when I apply t to this side, well, because it's a linear combination, I end up with the linear combination of what I get by applying t to these vectors. And what I get is multiply the vector by lambda, the corresponding eigenvalue. So I get a lambda 1 there, and over here I would get a lambda j minus 1. Okay, now this left-hand side is just lambda j vj. So I can achieve this in a different way. What I could have done is just multiply both sides of this by lambda j, and I would have ended up with the same left-hand side. So let's do that. Multiplying lambda j to both sides of star, I would have ended up with lambda j vj, and then here I would have a1 lambda j v1 dot 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 a j minus 1 lambda j vj minus 1. And now I can subtract them. Okay, subtracting, I get 0 on the left, the vector 0, right? Because lambda j vj cancels lambda j vj. And then over here, I end up with a1 lambda 1 minus lambda j v1. And then so on until I end up aj minus 1 lambda j minus 1 minus lambda j vj minus 1. Okay, but now, since vj is the first vector that can be written as a linear combination of the previous ones, that means that the previous ones have to be linearly independent, have to form a linearly independent set. So by our minimality assumption, the set v1 to vj minus 1 is linearly independent. Okay, fantastic. So now I have a linearly independent set of vectors. I have a linear combination of those vectors and it's equal to 0, right? But we know linear independence means that if you have a linear combination equal to 0, all of the coefficients have to be equal to 0. So this implies that ai times lambda I minus lambda j is equal to 0 for all I. For all I between 1 and j minus 1. But since lambda I is not equal to lambda j, for I not equal to j, right? Because remember, this is a distinct set of eigenvalues. We have ai equal to 0 for all I. But hence, so this for all I between 1 and j minus 1. But then from star, we see that vj is equal to 0. But vj is an eigenvector, and eigenvectors are not equal to 0. So that's a contradiction. Right, so that's how we'll use this linear independence lemma as a very useful technical tool for doing proofs. Okay, that's a good place to stop. So let's stop there for this time and pick it up there next time.